All right, we'll continue this session. In the last class, we completed the unit 1 and we started the next unit. The first topic which we started was spanning tree. So, just to quick refresh, spanning tree is a special kind of a tree. It has to be a connected graph for sure, and it's a subgraph of a given graph, and that subgraph should the spanning tree should cover all the vertices of the given graph, and it should be minimally connected. Okay. So tree itself is a minimally connected. So the spanning vertex should cover. It should have all the vertices of the given graph. So we saw a few examples yesterday. One of the examples is this. So we also saw a spanning tree for this graph, colored highlighted in green. The edges, all the vertices are covered, and it's a tree. There is no circuit, and it is minimally connected to given graph. So this again, the green color one is a subgraph of actual graph G, which which has all the vertices. So it's a spanning tree. So definitely, for a given graph, there is no as such only one spanning tree exists. There can be any number of spanning trees. So two I have already shown here. So we'll continue. In this example, it has B6 and plus 14 edges, I guess, 14 B6 and C8. Yeah. So there are 14 edges and 7 vertices. In these edges, few are named as P1, P2, P3, P4, and P5, P6, and the rest are all C1 to C8. So B indicates they are the edges of spanning tree. So they are called branches. Excuse me. So they are called branches of a tree. So naming convention as B, and the rest of the edges are chords. So they are not part of spanning tree. Since spanning trees are the largest trees among all trees in G, so in the last class I did mention, for a given graph, say there are 100 vertices complex graph, there can be so many edges, self loop, etc., and parallel. Definitely 2 to the power of e possible combination of subgraph can be made. So, and from those subgraphs, definitely trees can be made again. So, from a given graph, there can be so many trees can be made. In that, the point is, it should cover all the vertices and it should be minimally connected. So, can we say that the spanning tree is defined only for a connected graph? Of course, it is. Yes. It is only for defined for connected graph. If there is a graph with 2 components, means it's a disconnected graph. So, as part of definition of a spanning tree, it should cover all the vertices and minimally connected. So, if I want to cover all the vertices from both the components, but there is no connection from one component to the other, no edge. So in that case, it will become two components, and each component, if it is fully connected, of course, when we say component, it is connected. So it is connected. We can have a spanning tree for a component, and 2 spanning trees for both the components. And these trees are called kind of forest. So such, if a given graph has multiple components and each component have a spanning tree, so such combination of spanning tree are called forest. So, so there's a disconnected graph with k components. As I said, any number of components. Disconnected graph with k components has a spanning forest consisting of k spanning trees. A collection of trees is called a forest. That's the word forest is being derived there. Yeah. So steps to find a spanning tree in a connected graph. If G has no circuit in its own spanning tree, then if G has no circuit, then that is a spanning tree. The graph itself is a spanning tree. Circuit. I'm not telling about cycle or parallel edges. Circuit. There are no circuit. That itself is a spanning tree. If G has a circuit, in this example, yes, we have so many circuits. We don't know how many circuits are there. Probably more than the combination, more than 50 probably. Yeah. So in this example, definitely we have a circuit. Delete an edge. So we are just going through the steps to find a spanning tree. Delete an edge from the circuit. This will still leave the graph connected. So we should delete edge such a way that graph should not be disconnected. Graph should be connected. And check again after the deletion, spanning tree is existing. So if not, repeat this step until we find a spanning tree. So very simple procedure to find a spanning tree. So in a given graph,
Sir,
yeah.
could you explain a bit louder?
Am I not clearly audible? Let me switch off my
Like voice is low,
Yeah.
low, sir.
Am I audible now?
Yes, sir, fine.
Yeah. I was explaining about the steps to find spanning tree in a connected graph. First, check if that given graph has no circuits. If that is the case, that is the spanning tree. In our case, the example which I shown in the figure, we have so many circuits there. So in that case, we delete one edge such that it should not be disconnected graph. It should be connected graph. So choose appropriate edge while deleting. Only if the graph is connected, then can remove that edge. So after removing, cross-check again the given graph is become a spanning tree or not. If not, repeat this step until we find a spanning tree. And the constraint is every time when we remove, we should make sure that the graph is connected. So the edges which are getting removed are no more part of the graph. They are called chords. The final set of edges which will remain part of spanning tree are called branches, tree branch. So some of the properties of spanning tree, actually they are the theorems one. I will just consider as a property. So every connected graph has at least one spanning tree. If the graph is disconnected, definitely there is no point of tree itself. So forget about spanning tree. There is no connectivity at all from one vertex to other. No, it can have a tree, but it can't be a spanning tree because all vertices should be covered. Just a second. Yeah, I'm sorry for that. Yeah. So every connected graph has at least one spanning tree. That is one of the properties. The next property is with respect to any of its spanning tree. So as I said, in a given graph, we can have more than one spanning tree. So in such cases, in this case, there can be multiple spanning trees. So with respect to all of its, any of its spanning tree, a connected graph of n vertices and e edges has n minus one tree branches, right? So spanning tree itself is minimally connected. N vertices means n minus 1 um, edges which will part of a spanning tree, and these edges are called branches. So n minus 1 tree branches, and the remaining edges, that is the overall edges are E, then E minus whole bracket of n minus 1, so that is E minus n plus 1 are considered as chords. So yeah, and the addition of chords and branches will make the final edge count. So yeah, this is good enough for to find a spanning tree, and we'll quickly see one application of spanning tree, why it is required in such what situation. So we consider we have a farmhouse consisting of 6 walled plots of a land, as shown in figure. Yeah, 1, 2, 3, 4, 5, and 6. So 6 areas, and they are all walled. And these plots are full of water due to heavy rain. Probably, how many walls will have to be broken so that all the water can be drained out? So we have to remove X number of walls so that all the water which has been occupied in those plots has to be drained out. So in this case, very simple. We have n value, n equal to 10. This is 1, 2, 3, 4. I mean, all the there are no crossover. When I say crossover, 2 edges crossing over without any vertex. There are no crossover. So whatever the edge is connecting to other edge, that is the vertex, we can say. So if we count, vertex are n value equal to 10 and e value equal to 15. So with that example, we can say 15 minus 10 plus 1. We know E value and we know N value, and we know how many chords will be there. So chords equal to E minus N plus 1. Previously we saw that quick. So if I remove these chords, the water will drain out. So it will be minimum spanning tree. This example, if I remove the walls, such that it has to be a minimum. I mean, the whole plot should look like a minimum spanning tree. So the number of chords will be 15 minus 10 plus 1. Simple equation will get 6. So 6 number of walls has to be 6 number of walls has to be removed, and so that the all water which has been accumulated there should get drained out. Just a quick application. Yeah, before I will speak about this also. So few things about spanning tree and rank and nullity. We'll discuss more on this when we reach unit 4, just to have a look. So I have put this information. So rank of a G is nothing but the number of branches in any spanning tree or a forest of G. When I say spanning tree, it is for connected graph. When I say spanning forest, it is for a disconnected graph. So considering a connected graph, the component will be 1, right? So it is n minus 1. The branches will be n minus 1, minimally connected. Right? Hope everyone is getting that. N is number of vertices. It's a connected graph. The connected graph means only one component. Disconnected graph means multiple components. So in that one component, n minus 1. If there are more components, say k components, then the number of spanning tree branches collectively across components, k components, is n minus k. Okay, n minus k. That is the rank. So in general, we are saying that rank is n minus k. K equal to number of components. Previous case, the k was 1. So n minus 1. So if I have a graph with, I could have put some pictures here, but yeah, this holds good. I mean, you can figure it out. So it holds good for any number of components. If you try to take a disconnected graph and try to make a spanning forest across those components, and if we count the number of branches in this spanning forest, that is the rank, it is n minus k. And nullity is similarly the chords, e minus n minus e minus of n minus k, that is e minus n plus k. We'll discuss this more on this topic on upcoming units. That is the unit 4. And slide has been repeated. Okay, so before going into fundamental circuits, right? So Rishabh, take the attendance. 48 students are there. I hope.
Okay, sir.
Yeah, so many students will probably participate in a surprise quiz now. And there is a surprise quiz, SQ. So everyone log into your Google Classroom. Probably in few minutes I will assign. What is that? It will be a fun quiz. Hope so. Mm-hmm. Yeah, I have attached instructions and quiz also, JPG in that quiz. I just made it. So it is almost 150. If I upload to download some, time is 15 minutes. So considering the fact that by 210 should be good, no? To upload, to download, everything. So I'm giving full-fledged 20 minutes in this quiz. It's a quick one. So I will give you a graph. You need to find out if there is a Euler line present or not. If it is there, then what is that Euler line? And next is open Euler line, exists or not. If it is not, then no need to give any proof for that. If it is there, then you have to show that without any repetition. If you say yes and if you give the wrong answer, that doesn't carry any mark there. So be very cautious in giving your answers. Then for the same graph, is there any Hamiltonian circuit present? If there can be many, one is good enough. If there are many, one is good enough. Okay, and similarly Hamiltonian path and spanning trees. So we need to find Euler line, open Euler line, Hamiltonian circuit, Hamiltonian path, and spanning trees. These 5 things for the same given graph. Okay, I've given deadline for 15 minutes to code, means to figure out for the solution, and 2 minutes to upload. And output, whatever you write, you take a screenshot or take a photo, it should be start with your register number. And register number with should be fine. If you want, you can mention SQ1, surprise quiz 1. Okay. So yeah, I will assign now, and I will show the I just assigned. I will show what the graph is. We just saw this, and this is the graph. It's a simple, tricky graph. So need to find Euler line, open Euler line, Hamiltonian circuit, Hamiltonian path, spanning tree. Start with the easiest one, and so that you get a confidence to do the other. Yeah, time starts now. So it's 1:52. Yeah,
Sir,
yeah.
Can I get the class code? I was not in the classroom.
Sorry, come again.
Can I get the class code?
Class code.
Yes, sir. I was not in the classroom.
I'm new to this class code. Just a second. Let me.
Go to your Chrome, sir.
Okay. Classroom. Okay, this. Class code. It's CS321 class graph theory and okay.
They show up in that invitation link.
Invitation links. Okay. Now I get. Okay, now I get that. Okay. Fine. Only invitation link, right? So yeah, this is the class code CKQGBR7. If or hope now this is visible.
Yeah, thank you, sir.
So I'm displaying the question. This is the a simple and tricky graph. Find out and don't share the answers with your friends because it's a. I want everything should be fair. Quick evaluation and upload it. Can someone acknowledge that you received a quick assignment there in classroom? Yeah. Thanks for the confirmation, Ishita.